Swayam Prabha. Digital India. Educated India.
Welcome to the course on strength of materials. This is the first level course on deformable solids. Many concepts in this course are developed based on a simple tension test, starting from the concepts of stress and strain. The breakage of chalk at different angles to tension or torsion, prompting the determination of the plane of breakage, is used to develop the concept of stress vector and eventually the stress tensor. Key idealizations in this course are that the material is an elastic continuum, homogeneous, isotropic, and experiences small deformations. The stress strain curve is modeled as linear for small deformations. The main focus is to get the variation of the resistance to axial, bending, or torsional loads of slender members. The triangular variation of stress in bending has taken 400 years to get established. Photoelasticity can reveal the stress as beautiful fringe patterns in color. Being an experimentalist, conscious effort is taken to include as many experimental results to reinforce the concepts better. Brittle coating is an elegant experimental method to establish that the principal stress directions are mutually perpendicular. Depending on the strain level, one has to select appropriate methods for strain measurement. The strain gauge technique is very useful for many standard applications, and digital image correlation is useful for large deformations. Concepts of principal stresses, Mohs circle of stress and strain, thermal strains, and number of elastic constants required to characterize any material form a part of this course. Development of shear in beams is very subtle to understand, and this is systematically developed in this course by performing experiments on layered beams. Although shear stress variation over the depth of the beam is parabolic, near load application points this can be quite different, and the strength of material solution is inadequate. This is well captured by a photoelastic experiment. Shear stress in open sections such as I-beams, concepts of shear center and unsymmetrical bending are discussed in this course. Engineering analysis of beams based on Fleischer formula and superposition methods to find the stress tensor in combined loading of tension, torsion, and bending are well covered. Various methods to determine deflection of beams, including the energy method of Castigliano, are presented. Energy method is extended to get deflection of a tension spring and shear deformation in beams. Development of finite element method to solve real-life problems has also been highlighted. I am Professor Ramesh from the Department of Applied Mechanics, IIT Madras, with 34 years of teaching experience. I hope you will assimilate the concepts of strength of materials better with extensive experimental and multimedia content embedded in this course. Failure theories are based on simple tension tests, and use of principal stresses come in handy to predict the failure behavior of actual structures. Failure of ductile materials is predicted either by Tresca or von Mises theory, and brittle materials fail by Moore's theory. Historical perspectives on the development of these theories as well as failure locus are very effectively brought out through appropriate animations. To investigate stability, one has to work on deformed coordinate systems. Although mathematical development is restricted to column buckling, the importance of buckling as a failure mode in the presence of compression, such as in bending, shear, or torsion, is well brought out. The course development is such that the students can easily grasp and adopt these concepts for application courses such as design of machine elements and higher level courses on continuum mechanics. Thank you.